Find the perimeter of triangle ABC if AC is 18, YC is 5, and XB is 9. So, remember, on Friday we learned 3 theorems. One of them I nicknamed the ice cream cone theorem because I thought it just kind of looked like an ice cream cone. When you've got a point outside a circle, an external point, and you draw both tangents from that point, those tangent segments have to be the same exact length. So that's what we're going to use there. Way to answer first, Jenny. There's not a word bank on the quiz. Thanks for asking. All right, so we know that if this one's 9, then that one's 9. If this one's 5, then the other purple one is 5. And then we do 18 minus 5. 13. 13. And now we can find the perimeter of our circle. Okay, let's go over the homework. Chords was the name. Chords. Number 20 on the chords worksheet. An equilateral triangle with sides of length 10 is inscribed in a circle. Find the distance from the center of the circle to the side of the triangle. So this is kind of like old stuff from a different unit. So it's equilateral, so we know the angles are 60. The side is 10. We want to find the distance from the center of the circle to the side of the triangle. So we're really finding the apothem of the triangle. So this is kind of just old stuff. We can draw ourselves a radius. I'm trying to think of how we would use chords in this, but I'm not sure we're going to get any better of a result using chords. Well, hey, we can use one of our new theorems. When a radius is perpendicular to a chord, it cuts the chord in half. So 5 and 5. And then we've got 60, 30. So we've got 5 divided by root 3, which is 5 root 3 over 3. So that goes 10 root 3 over 3. Not that that matters. That's all there is to it. It was really just finding the apothem of the triangle. But I was trying to tie it into the lesson. So when a radius is perpendicular to a chord, it cuts the chord in half. That was one of our theorems yesterday. What else from this worksheet? 25 through 28. So we learned a lot of theorems yesterday. One of them was that congruent chords intersect congruent arcs. So we know, well, there's a lot going on here, but first of all, we know that this radius is perpendicular to this chord. So we know that chord has been bisected. So we know 9, 9. Now we know OQ is congruent to MR because both of those segments are 18 units long. Since both of those are 18, they're congruent chords. Congruent chords intercept congruent arcs. So now we know that arc QO is congruent to arc RM. They're congruent. How much is arc RM? Well, that arc got cut in half because the radius is perpendicular to the chord. We're using all of our theorems. So we've got 104 for arc RM. Therefore, Arc OQ is also 104, but it gets cut in half, so 52. UT is going to be the same as the other side because we've got a lot of symmetry going on here. So UT is also 5, OQ 104, and ROM. So, since there's 3 letters, it's a major arc, so you have to take the long way around. R to O to M. So, how are we going to find that? R-O-M. So we know that it's 360. 360 minus the part we don't want. 104. Very good. Yep, you got it. Good job. 256. Anything else from this homework? Okay, so Yeji's asking a question from the basic terms worksheet. Yeah, when a segment's endpoint is the center of the circle, it's sometimes a radius. There's a segment whose endpoint is the center of the circle. Let me draw another segment whose endpoint is the center of the circle. That one. Let me draw another segment whose endpoint is the center of the circle. That one. So now I've just drawn plenty of segments that are not the radius whose endpoint is the center of the circle. All right, let's move on to today's lesson. Central and inscribed angles. No, Jenny, we're not. We're already done with our solid unit. Central and inscribed angles. So, we've already talked about a central angle. It's an angle whose vertex is the center of the circle. And when we were doing vocab, we also talked about how the measure of the central angle, like if that's a 33-degree angle, is equivalent to the measure of its intercepted arc. So the measure of angle ABC is equal to the measure of arc AC, whatever arc it opens up to. An inscribed angle. So an inscribed angle, this is good, this could show up on your quiz today, is an angle whose vertex lies on the circle. So this angle, the vertex of this angle is B, the vertex is on the circle, the point. What arc does that angle intercept? Just think about if the angle were to chomp down on that circle, what arc would it eat? So this, AC, is the intercepted arc. So now we're going to look at what the difference is between a central angle, angle A, and an inscribed angle, angle B. Which one do you think is smaller? Right? Okay, so think of it as a bow and arrow. As you're pulling that away and away and away, your angle gets smaller and smaller and smaller. I forget if I have a picture of that. No, I don't have a picture of it. Okay, I already gave away the answer. But let me show you something real quick on here. Not that one. So here's a sketchpad file of a central angle and an inscribed angle. Notice the central angle is 94 and the inscribed angle is 47. When you divide them, we're getting 0.5. I'm going to drag this around and see if that stays at 0.5. Oh, my alignment's off. Are the angles changing? No. Let me move the arc around. Maybe, no. Whoa, the angles are changing, But is the inscribed angle still exactly half? Is the 0.5 changing? No matter what I do, the inscribed angle is half of the central angle. So angle D is half of angle A, 34 and 17, no matter what I do. I can even change the size of my circle. Maybe. There we go. I can change the size of my circle, but it doesn't change the fact that the inscribed angle is half of the arc. So, good to know. An inscribed angle is half of a central angle, and therefore it's half of the arc. So go ahead and write that down. So, if the arc is 80 degrees, then this angle is 40 degrees. We got it? Inscribed angle, half the arc. Not too bad. Let's dive right in and try some. We're going to go pretty quickly because I don't want you to run out of time for your quiz, like happens to us sometimes. ADC is 152. So be careful. The central angle is equal to the arc, and the inscribed angle is half the arc. So 152 divided by 2, 76. Measure of arc, ABC, that's a major arc. So that's 360 minus 152. 208. And 152 and 76. It's way too easy. Okay. Let's try this one. ACD is 62. Arc CD is 58. And arc BC is 47. Now, what do you think is true when two inscribed angles are opening up to the same exact arc? What do you think is true? When two inscribed angles are opening up to the same arc. They've got to be equal, right? Because if you divide something by 2, and then you divide something by 2 again all over again, you're going to get the same number both times. So, take a look at this angle and this angle. Do you agree that they're both opening up to arc AD? They're both chomping on arc AD? So angle B is going to have to be the exact same as angle C because they are both intercepting the same arc. So, angle ABD is automatically 62. 62, 62. ADC, well, first we have to find AD. We take 62 and we double it. 124. And then we can find ADC, 124 plus 58. 182. We okay so far? Just adding things together? Stop telling me what it looks like and start solving. And now we need BDA, angle BDA. An inscribed angle is half of its arc. So you need to find the missing arc, and then you need to divide by 2 because an inscribed angle is half the arc. So who's going to get it first? Find that missing arc. Find arc AB. Albert wins. When you subtract this number and this number and this number from 360, you get 131. When you divide 131 by 2, you get 65.5. All right, let's keep going. Oh no, there's no angle measures here. What are we going to do? You can't put as your answer x is 1/2 y because we want to get actual numbers. Well, we can do even easier than 6y equals 360. We can say 3y equals 180 because that is a semicircle. So what does y equal? Yep. So y is 60. And once we know y, we know x. Not so bad after all. Just had to be a little tricky there. All right, a little bit more. I'm just going to go right into this theorem because I'm afraid we're running out of time. If an angle opens up to the diameter, if an angle opens up to a diameter, it is a right angle, no matter what. No matter where I put this point. I could put this point right here. If an angle opens up to a diameter, it is automatically a right angle. And why is that true? Because that angle is opening up to 180. What's 180 divided by 2? Every time it's 90. So if an angle intercepts a semicircle, it's always a right angle. Okay, last thing, and I'm just going to throw this one at you too. I'm sorry we don't have time to discover it. In a quadrilateral, the opposite angles are supplementary. And we're not used to that because in our parallelogram unit, opposite angles were congruent and consecutive angles were supplementary. But just think about it. Angle B and angle D, together they open up to the whole circle. The arcs they intercept, between B and D, they intercept the whole circle. Well, to find the measure of an inscribed angle, you take the arc and you divide by 2. So together, these have to add up to 180 because they're the whole circle divided by 2. So when a quadrilateral is inscribed in a circle, only when it's inscribed in a circle, the opposite angles are supplementary. Okay, we're going to skip that. I'm sorry because we're running out of time. Oh my goodness, I didn't realize there were so many theorems. This is not a separate theorem, so you don't even need to write it down. When you've got a tangent and a secant, because the vertex is on the circle, you're going to treat it just like an inscribed angle, just like one. So if this arc is 200, then that angle is 100. You treat it just like an inscribed angle, even though you don't call it an inscribed angle. Treat it just like one. Okay. We are not going to have enough time to do these examples. Go ahead and start your quiz. DF is tangent to circle O. So we know when a radius meets a tangent line, you get a right angle. So you can put a right angle right there. And now we need to find all these missing things. DOF. Well, we know if this is 90 and that's 33, then we can do 90 minus 33 and get 57. DOF. Yep. All right, arc BC. Well, if we know if this arc is 110, then this angle is 110 because it's central angles. And now we can add up all those numbers and subtract from 360. 360 minus 80 minus 57 minus 110 minus 90. And we get 23, which makes that arc 23. Arc DE is the same as its central angle, 57. And arc DBA. It's just the addition of these three arcs, 80 plus 23 plus 90. That one wasn't too bad. All right, next one. So we've got an inscribed isosceles triangle. We've got a tangent line, but we don't have a radius, so don't add a right angle. Let's start in this triangle right here. We know if we have the vertex angle of a triangle, we can subtract it from 180 and divide by 2 to find the base angles. So our base angles are 65, 65. So we've got Z. Then take a look at how Z opens up to Y. Z opens up to Y. Z is an inscribed angle. We just learned inscribed angles are half the arc. So if we double Z, we're going to get our arc. And lastly, we have to find X. Now, what we can do is we can find the arc that X is opening up to. What arc is X opening up to? Well, X is opening up to this arc right here. What's the measure of that arc? Well, it's this angle doubled. That arc is 100 degrees. And then we treat it like an inscribed angle. Inscribed angles are half their arc. So 100 divided by 2 is 50. We also remember that any two angles that are inscribed and open up to the same arc are going to be the same measure. So those 50-degree angles, they're both opening up to that arc that's 100 degrees. So they're going to both be 50. All done.